So
I had to cut some last year.
Yeah.
So remember, there's a test this week on Unit 8 on Thursday and Friday. Thursday will be no calculators. Friday will be calculators. Any questions on that? Wednesday, the plan is to go over the personal progress checks. So make sure you're taking a look at those before that. It would definitely be most beneficial to you if you do that. And they're due Thursday morning. Okay? Any questions? Okay, so the only topic we have left in the next 2 days we're going to talk about this topic is volumes, finding volumes. And it's just another application of integration. So you should be able to answer any AP question that you come across, except for questions that have the word volume in them. After these 2 days, those will be no problem either. Okay, so finding volume. So let's just go back in time for a second and remember how we first found areas. Okay, so remember if you're trying to calculate the area under a curve. Okay, so like say the curve looks like this, x, and you're trying to calculate the area between A and B. Okay, if you remember what we did is we constructed little rectangles of a particular height. Maybe we used the left-hand endpoint to determine the height of the rectangles. Maybe we used the right-hand endpoint. Maybe we used the midpoint, right? But we did these little rectangles. So we had like a rectangle like this, and a rectangle like this, and we just kept doing that, and we added up all of those areas, right? So let me just finish drawing here. I'm just randomly picking rectangles, whatever. Okay, so we figured out that the area is equal to the limit as n goes to infinity. Remember, n was like the number of rectangles. And then we took the sum from k equals 1 to n of each of those rectangles' areas, which ended up being like f of x sub k. And this is like each x sub k was given by, maybe it was the left-hand endpoint of that little tiny interval, or maybe it was the right-hand endpoint, or maybe it was the midpoint, or whatever, but it was some x value in that little tiny interval. Like if we're calculating this rectangle right here, we take some x value in that little tiny interval, use that as the height of the rectangle, and then delta x is like the width of the rectangle, which if they're equal width rectangles, then this just ends up being like b minus a divided by n. Remember that? We did this, and then we figured out that this is actually equal to the integral from a to b of f of x dx. So what I want to point out is basically the integral is like the continuous infinite example or form of summation. Like if you take the summation of an infinite number of little tiny thin things, this kind of turns into an integral symbol. And the delta x, width of the rectangle, kind of turns into dx. Okay? And then this is still the same, f of x, right? So that's kind of how I want you to think of this. Like this part of it is really like this part of it, okay? And the delta x and the dx, they kind of like go together. And then f of x and f of x kind of is the same, okay? So it's sort of the same development when you think of how to calculate volumes, okay? So for example, suppose you have a solid three-dimensional figure, Okay, so suppose you have a 3D solid where, let's suppose the base is the region bounded by y equals x squared, y equals 0, and x equals 4. So if I graph that, that's no problem. So the region I'm referring to is like this kind of like almost triangular shaped region like that, right? That's the base of the solid. And suppose that cross section, so picture this triangular shaped figure like sitting on a table, okay? And suppose that cross sections perpendicular to the x-axis are squares. Okay, so you have like, for example, if I look at, this is the base of my solid, I have a square coming out of the board that looks like this, right? Picture that in 3D. There's a square coming out of the board. And there's a square coming out of the board here that looks like this. Right? And at every single point, there's a square coming out of the board. Okay, so hopefully you can sort of envision what this looks like. It's super weird, but it almost looks like a cone shape, but there's like angles, right? It tapers down to a point, but then as you go, I mean, there's definitely going to be like vertical walls. If this was on the table, it has like vertical walls, but they curve, and the top curves. It's super weird, but can you sort of picture this solid? It's sort of hard to draw it, obviously, but any questions about what the solid kind of looks like? Okay, so if we're trying to calculate the volume of this solid, we could kind of do the same thing that we did to calculate the area of a region. We could just consider this to be like little tiny thin, like rectangular prisms. You know what I mean? Like think of this as like a little thin box, like a pizza box coming up out of the board, right? And we could just add up all of these little pizza boxes, okay? Well, think about what you would have. You would have the volume would equal the limit as n goes to infinity. Again, n is the number of little thin boxes that we're making, right? Of the summation, k equals 1 to n. Now, if you think about what the volume of one of these little boxes would be, right? It would be f of xk squared. That's like, if you look at this picture, that would be like length times width, and then times the height of the box, if you think of it as like a pizza box, would be like delta x. Does everyone agree? Like, this is like length times width times height when you picture a pizza box. The length and width are both the same, so that's why this is f of xk squared, but the width is just that little tiny change in x. Which again, if I'm taking equal width things, this is from 0 to 4, this would be like 4 divided by n, right? Would be like the width of each box. Everyone cool with what I have so far? But remember what I set up here. Like, you can think of integration symbol as being like the continuous infinite example of this part of it, right? So what this ends up being is the volume is actually equal to the integral from 0 to 4 of f of x squared dx. Which I know what f of x is, it's just x squared, right? That's the height of the function. So this is really just the integral from 0 to 4 of x squared squared dx. It's just x to the 4th. So this, I mean, I'm gonna do it in this one case, but I'm not gonna do it every time, just to save a little bit of time. This is gonna be x to the 5th over 5, 0 to 4. Which is 4 to the 5th over 5 minus 0. Whatever that is, let's do it, why not? So 4 to the 5th is 1024. So this is 1024 fifths. That's the exact volume of that weird cone-shaped, sort of cone-shaped thing that we created. It's 3D solid. Okay? But the bottom line is, okay, so basically what goes here as an integrand is the area of a typical cross-section perpendicular to the axis of integration. Now, what's that? Axis of integration. The axis of integration is the x-axis in this case. It's the x-axis if these are both x values, the limits of integration, and this is a function of x. Then the axis of integration, you're integrating on x values. So we're going to be looking at cross-sections perpendicular to that. Okay? So this is not inconsistent with our area stuff, because if you look at our area stuff, like what went in here, like this integrand up here, ended up being like the height of a typical slice, right? This is like the height of a typical slice perpendicular to the axis of integration. So I'm just basically taking what we did in 2 dimensions here to calculate area, I'm just extending it, and we're doing the exact same thing for 3 dimensions here to calculate volume. Does everybody see that connection? Now, what could vary in these problems is a couple things. Obviously, the region that's the base of the solid could change, right? And then what the cross-sections look like could change. Maybe instead of the cross-sections being squares, maybe they're like semicircles coming out of the board. Well, what if that was the case? All right, so what if I had same base, which is this little triangular thing like that, same base. But this time, suppose that cross-sections perpendicular to the x-axis are semicircles. Okay, so again, I could try and draw it a little bit, but if I just draw like one semicircle here, I mean, picture a semicircle coming up out of the board where this green line that I've drawn here is like the diameter of that semicircle. So there'd be a semicircle coming up out of the board. This is 3D coming this way, not drawn sideways. It's coming this way. Hard to draw, but you sort of see how that would look. There'd be another one kind of like this. That. There'd be a little tiny one right there that looks like that. This would be even more like cone shaped. It's like a cone that isn't like a right cone, and it's like split in half. Can you picture that? It's like half a horn. Okay? Everybody can envision that? All right. So in this case, the volume would be, right? This is from 0 to 4 again. Right? It's the same base as before. So this would be the integral from 0 to 4 of the area of a typical cross-section. Well, a typical cross-section is a semicircle. What's the area of a semicircle? 1/2 pi r squared, right? So this is 1/2 pi r squared dx. Now I just need to figure out what r is. Well, r is really just half the height of the function at any given point, right? So this is the integral from 0 to 4 of 1/2 pi times 1/2 f of x squared dx. Integral from 0 to 4, 1/2 pi of x squared over 2 squared dx. That's the answer. Whatever this integral ends up being, that's the exact volume of that half a cone shaped thing. Everybody understand what I'm doing here? Obviously, this can be simplified. Like if I was actually going to evaluate this, and this was a non-calculated part of the test, I would take all the constants and move them out of the integral completely. So this denominator is really a 4, right? So I would write this as pi over 8 integral from 0 to 4 x to the 4th dx. That's what I would do if I was actually evaluating this. That's how I would do it. It's a lot simpler to integrate that than that, right? Okay. Let's try another example. So let's change the base. Let's say the base is the base of the solid is the region bounded by y equals x squared minus 2 and y equals negative x squared. So, okay, that seems like it's going to work. So let's draw it. So we have negative x squared looks like this. X squared minus 2 looks like this. So this region right here is the base of the solid. Shaped like an eye. And let's suppose that the cross sections perpendicular to the x-axis are, let's say it's isosceles triangles. Isosceles right triangles with a leg in the xy plane. I mean, you can see like the possibilities are endless. They could give you any cross section they wanted, right? But it's the same process. All right, so let's try and envision this. We have triangles coming out of the board where it's an isosceles right triangle, which is just like this, right? That's an isosceles right triangle. But this leg right here is like on the XY plane. So the triangle comes up out of the board like this. That's the right angle. That's a typical cross section, right? Isosceles right triangle coming up out of the board.
I have a question.
Yeah,
Could it also be like the hypotenuse on the XY plane?
they could. Yeah, let's do that next. Great idea.
I didn't see that you said,
Yeah, the leg is in the XY plane. Yeah, they definitely could have it be so that instead, don't draw this, instead it's coming up out of the board like this. That's definitely a possibility. We'll do that next. I think it's harder to do it that way. All right, so what do we need here before I go any further? What? Yeah, I need points of intersection because I need limits of integration, right? I need A and B. So I need to do that. So this is just going to be x squared minus 2 equals negative x squared. So 2x squared equals 2. X is plus or minus 1. Okay, so now I have limits of integration, plus or minus 1. This point is negative 1. This point, positive 1. And if this was a free response question, you get a point for finding the points of intersection correctly. I mean, that would be worth a point. So this volume would be the integral from negative 1 to 1 of the area of a typical cross section. What's the area of a triangle? 1/2 base times height. So this is what I would suggest that you write every time. Like, write the formula for the area of a typical cross section. In this case, it would be 1/2 base times height, dx. Now, all you have to do is just replace base and height with what they actually are in terms of x. So what's the base? Well, in this case, I know the base and the height are equal, right? Because it's an isosceles right triangle. Well, what are they in terms of x? Perfect. Yeah, it's just the difference between the top curve and the bottom curve, right? That's that height is top curve minus bottom curve. We know that from before. So this is just going to be the integral from negative 1 to 1 of 1/2 of negative x squared minus x squared minus 2 squared dx. Squared because it's base times height, and base and height are both the same amount. This is the exact volume of the figure that we formed, a 3D figure. Is this kind of making sense? Let's do the example that John suggested. Same base. Base is that same eyeball shaped thing. And this time, suppose cross sections perpendicular to the x-axis are isosceles right triangles. Whose hypotenuse hypotenuses are in the xy plane. All right. Again, here's -1, here's +1. But now the little sample triangles are coming up out of the board this way. So we have to find a formula for that. How do you calculate the area of this triangle? I mean, yeah, it's 1/2 base times height if you flip it around, but that's not really convenient in this case because this is the length we know. This is negative x squared minus x squared minus 2. That's the length we know. We don't know these lengths necessarily.
Well, it's just divided by radical 2.
Okay, that's one thing we could do. We could just say that these are actually going to be that divided by radical 2. So I could write that out and then just take 1/2 of that amount squared. That definitely would work, 100%. What's another thing we could do though? I know you can't read my mind, but maybe someone's thinking the same thing I was, because that's not what I was thinking in terms of my first impulse here. Well, that would actually give us the same answer that Paul said. Like if we say like let this be like b, and this is also b, do the Pythagorean theorem, you're going to get b equals this divided by radical 2. You're going to get the same result. That's what I was thinking. Yeah, I was thinking let's just like if I just draw that in, I know that this and this are the same, right? So if I'm trying to do 1/2 base times height, the base is this amount, and the height is half of that amount. You know what I mean? So that would make it a little bit less work, maybe. I don't know if it's really less work. It's just a different way to do it, right? So this would end up being the integral from -1 to 1. And I'm going to follow my process, 1/2 base times height dx. I know I get annoyed personally in science or something like that where I got to write the formula out first and then plug stuff in for it. But I honestly think in these volume problems, it's easier if you do that. It's a lot easier to keep track of what you're doing. Okay? So I'm just suggesting that you do that in these volume problems. So this is going to be integral from -1 to 1. 1/2 base, which is this, negative x squared minus x squared minus 2. Times the height, which is half of that. Well, I mean, I could like simplify that, right? Like think about it. If the height is half of this amount, I could just square that and square that. Done. Right? Because really, what I would have is I'd have, if I didn't square it, I'd have 1/2 of negative x squared minus x squared minus 2. Like I'd have all that stuff, but I'm just suggesting we can just get rid of that by squaring the 1/2 here and squaring this expression there. You get the same thing. Does everybody understand that? So there, that's the area. I mean, if you think about like things they could say the cross sections are, like possible cross sections. Because that's really the only hard part about these volume problems is like figuring out the geometry behind what's the area of a typical cross section. That's really the hard part. Okay, the rest of it's the same stuff we've been doing. Finding points of intersection. Those are our limits of integration. Finding height, which is just the difference of top minus bottom, and so on. The cross sections is the geometry part. That's the part that's different every time. It could be a square, like we did. First example. Could be a semicircle. We did in the second example. It could be triangles. And again, there's lots of variations. They might say it's a right triangle where the height is twice the base, something like that. I mean, you'd be able to do that also, right? Or they might tell you it's an equilateral triangle. You'd be able to do that, you know? So there's lots of possibilities if it's an equilateral triangle. It could be rectangles. Like they might say, it's a rectangle where the part that comes out of the board is twice as long as the part that's on the xy plane. It's just base times height. It would be the height of the function, which would be like f minus g, and then the height of the function would be 2 times f minus g. Okay, so it would just be the typical cross section here would just be base times height. Okay? I mean, those are basically it. Like, those are the only possibilities. Like, if you think about other geometric figures, they're not going to make it crazy. They're not going to say, like, coming out of the board, you got octagons or something weird like that. It's going to be like one of these things. Okay? That's really the only things that you're likely to see. Is everybody okay with this? It's a little bit like there's a lot to wrap your head around. On each problem, you really have to think about the geometry behind it and picture the figure so that you know what the area of a typical cross-section is, right? But the stuff in black here, like that's what they're going to give you. They're going to tell you what the base is. They're going to tell you what cross-sections perpendicular to the axis of integration are, and then you just go from there. Okay? Any questions? Yeah, John.
Is there gonna be like estimations for these, like LRAM or RAM or something?
Great question. No, that would be way complicated. Like if they said, approximate the volume by using like rectangular prisms of width 2, that'd be crazy. It'd be a lot of work. So no, I've never seen a question like that. I mean, they could theoretically do that, but it would be kind of like mean. And I've never seen them do that. It'd be really time consuming. Okay. All right, let's do a quick problem of the day. I got a multiple choice question. And this is actually on the calculator part, but I don't really know if that really helps that much. Here's the question. This is the calculator part of the exam. I think this one's pretty easy. Who has an answer? Anybody? Yeah, what do you think? You think it's A? You think it's C? C, what do you think? C. Anybody have a different answer other than A or C? So what I try and do, whenever they ask which of the statements must be true or which of the statements must be false, for me it helps to try and think of like counterexamples. Like if they're asking you when it's true, think of a scenario where it wouldn't be true. Like in this case, they're telling you 10 is, or f of 2 is between 10 and 18. I mean, the function, if f of 1 is 10, let's draw a little picture. If f of 1 is 10 and f of 3 is 18, that doesn't necessarily mean that it goes from here to here. It might like dip down, right? So you could have a function that goes like that, in which case f of 2 is not between 10 and 18. So that rules out A. It also rules out B. Here's a perfect example. Nowhere up here do they say that it's like continuously increasing. So you could just have this as a counterexample for B as well. C, f of x equals 17 has at least one solution in the interval from 1 to 13. So 17 is like here somewhere, right? So how do I know that f of x equals 17 has at least one solution in that interval? IVT, right? Intermediate value theorem. We have a continuous function. There's no way it can get from here to here, from 10 to 18, without crossing 17, because it's continuous. So it's this one, definitely by IVT. If you look at the other choices, what are they trying to fool you into using in part D? MVT. Why isn't it MVT in this case? Yeah, so that's one reason why it doesn't work, because when you take f of b minus f of a over b minus a, you get 4, not 8. What's another reason why it doesn't work? It doesn't say it's differentiable, right? MVT only works for differentiable functions. For all we know, suppose this even said 4, for all we know, the function goes like this. Nowhere between here and here is there a point where the derivative is 4. Here the derivative's greater than that. Here the derivative's less than that. Nowhere in there it's undefined. So nowhere here would it be true. So there's 2 reasons why that doesn't work. And then what's this all about? What are they trying to get you to do there? Not f. Oh, f of 3. Oh, I get what you're saying. But then they would have written 8. Yeah. No, I think what they're trying to get you to do, again, is kind of like the same thing that they were trying to get you to say in A and B. If this was increasing, this would definitely have to be true. Because if you know that it's 10 here and 18 there, and you're taking like rectangles, you know, of varying heights, like the minimum that it possibly could be would be 20, for sure. Do you agree? It has to be greater than 20. Why doesn't it have to be true though? Yeah, you can have the function start here and be like, ooh, well, there we go. It's not 20 anymore because you got all this negative stuff, right? So that's why. Okay. Any questions on that? So this is another example. On average, you have 3 minutes to do calculator questions. This question should definitely not take you 3 minutes. Okay, so you don't want to pace it out where you're like, I'm going to spend 3 minutes on every question no matter what. Don't do that. All right, if you can answer it quickly and move on, because there's going to be questions that it's going to take you 4 minutes or whatever, you know? Okay. You guys are the bomb, as us kids say nowadays.